Today we're going to talk about absolute convergence. We say that a series, sum from n equals 1 to infinity of a sub n, is absolutely convergent if the series sum from n equals 1 to infinity of the absolute value of a sub n is convergent. In other words, in the original series, terms could be positive, terms could be negative, some could be positive, some could be negative, they might all be negative, whatever. If you take the absolute value of each term, in this series, sum from n equals 1 to infinity of the absolute value of a sub n, this series has only positive terms. The name absolutely convergent seems to sound like it's a lot stronger than just being convergent. And we will see that that's correct. But first, it might not be totally obvious that an absolutely convergent series actually does converge. So here's the question: must an absolutely convergent series, sum from n equals 1 to infinity of a sub n, actually be convergent? In other words, if the sum of the absolute values converges, must the original series converge? And it would certainly seem to make sense. Why? Because this is a positive term series, the sum of the absolute values. The partial sums just get bigger and bigger and bigger. They're increasing, as the partial sums are for any positive term series. Convergence for the sum of the absolute values means that these partial sums are bounded. For the original series, some terms may be positive, some terms may be negative. When you create partial sums, you look at A1 plus A2, A1 plus A2 plus A3, etc. The positive and negative cancellation that might occur in here should just keep the size of these partial sums under control. Now, it's not quite enough just to say the size is under control so that the size of the partial sums here is smaller than the size of the partial sums here. We actually need the partial sums to have a limit. And so that technical difficulty makes it so it's not totally obvious that these partial sums converge, even though the cancellation would seem to make it seem easier that they do converge. And as I already said, it will turn out to be true. There's a very simple and elegant argument that tells us that the answer is yes. So, must an absolutely convergent series be convergent? The answer is yes. If a series which is not absolutely convergent, but converges anyway, is called conditionally convergent. Let me show you the argument I was talking about earlier. So let's assume a series is absolutely convergent. What does that mean? Then the series absolute value of a sub n converges. Here's the really elegant part of the argument. Any term a sub n might be positive or negative, but if I add its absolute value to it, what can you say? Well, if it's positive, if a sub n is already positive, you just, when you add the absolute value, you get double the original term, which is the same as twice the absolute value. If a sub n is negative, the absolute value is positive, and when you add the two together, they cancel, and you get 0. So we can write this inequality that a sub n plus the absolute value of a sub n is always between 0 and twice the absolute value of a sub n. What's weird about this inequality is it will always be either all the way at the left or all the way at the right. It'll always be either 0 or exactly twice the absolute value of a sub n. That's for any particular n. Now, when you have a series like this, some terms might be positive, and you would have this a sub n plus the absolute value of a sub n equal to twice the absolute value of a sub n on the right, and for others, it'll be equal to 0. But for all of them, it's between 0 and twice the absolute value of a sub n. In other words, this is a positive term series and its terms are dominated in size by the terms from this series, twice the absolute value of a sub n, which converges. This series is just exactly the same as this series, only each term is multiplied by 2. And anytime you have a series which converges, doubling all the terms means it'll still converge. If this series converges to some number s, when you double every term, it will just converge to 2s. So here you have a positive term series. Each term is no bigger than this, and by the comparison test, this one converges. We're comparing this series with this known convergence series, this sum of a sub n plus the absolute value of a sub n converges. And remember, there should be parentheses here because you're summing up all of this stuff. Now, here's the trick. We know that this series here, the sum of the absolute value of a sub n, converges, and now we know that the sum of a sub n plus the absolute value of a sub n converges. When you have two convergent series, their difference also converges. So the sum of a sub n plus the absolute value of a sub n minus the stuff up here, the absolute value of a sub n. Since each one of these is convergent, the differences will also be convergent. And of course, those differences are exactly a sub n. And so thus, this new series converges. And that's what we wanted. So an absolute convergent series really is convergent. And even more so, it's convergent really nicely, because a convergent series which is not absolutely convergent can do weird things. It's called conditionally convergent, and we'll see an example of that coming right up.